Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Indefinite Integrals lecture 3. In this lecture we'll be continuing our discussion of substitution. Okay, so let's begin our lecture with this example. We have integral dx upon cos x minus sin x. Now whenever I see something of this sort, basically a sin x plus b cos x. In such a case, the first thought that comes to my mind is to convert this into a single sine or single cos. Okay, so how do we do that in this case? We have integral dx upon cos x minus sin x, right? So what we can do, we can multiply and divide by root 2 over here and take this root 2 outside this integral. So we'll be getting 1 upon root 2 dx upon 1 upon root 2 cos x minus 1 upon root 2 sin x. Now 1 upon root 2, this one can be written as cos of pi by 4. This one can be written as sin of pi by 4. So what we have got, cos pi by 4 cos x minus sin pi by 4 sin x. That is cos a cos b minus sin a sin b. So that basically becomes 1 upon root 2 integral dx upon cos of x plus pi by 4, right? Cos a plus b is cos a cos b minus sin a sin b. Now this can be written as 1 upon root 2 integral sec of x plus pi by 4 dx. Now this has become your standard integral, right? We have already derived the integral of sec theta, right? So you can use that formula to find out the integral of this one, right? Now, if you remember from derivatives, we studied some standard substitutions and we said that we'll be reviewing them once again in integral calculus, right? So here we are using them once again. And the main idea is to convert the complex looking expressions and functions into simpler ones, right? So the first one over here is under root a square minus x square. And the substitution we are going to use over here is x equals to a sine theta or a cos theta, right? So if we take x equals to a sine theta, this would become a square minus a square sine square theta, right? Now we can take a as common and we'll be getting 1 minus sine square theta. This actually becomes a times under root cos square theta. So this is a times mod cos theta, right? So we have got a very simple expression out of this complex expression, right? So in this case, a sine theta or a cos theta. For second case, a tan theta or the other pair is a cot theta. And for this one, a sec theta or a cosec theta. But for this last case, we'll not be using a square sine 2 theta. Why? Let's see. So let's say if we are taking x square equals to a square cos 2 theta. So we have under root a square minus a square cos 2 theta upon a square plus a square cos 2 theta, right? Now a square, a square, a square, a square gets cancelled from both numerator and denominator, right? So we'll be getting under root 1 minus cos 2 theta upon 1 plus cos 2 theta. Now we know that 1 minus cos 2 theta is 2 sine square theta and 1 plus cos 2 theta is 2 cos square theta, right? So 2 gets cancelled out. So what we have got under root tan square theta, again mod tan theta, right? So we have got this simple expression over here. Now let's use the other case. Now the other case is a square sine 2 theta, right? So we have got a square minus a square sine 2 theta upon a square plus a square sine 2 theta. Now a square gets cancelled out from both numerator and denominator, right? So we'll be getting 1 minus sine 2 theta upon 1 plus sine 2 theta, right? Now this can be written as sine square theta plus cos square theta minus 2 sine theta cos theta divided by sine square theta plus cos square theta plus 2 sine theta cos theta, right? So what we have done is we have converted this one as sine square theta plus cos square theta and sine 2 theta is 2 sine theta cos theta, right? So what we have got is cos of theta plus pi by 4 whole square divided by sine of theta plus pi by 4 whole square, right? So ultimately we have got cot of theta plus pi by 4. Now this is not a very standard expression, right? So in that case what we were getting tan theta, simple tan theta. In this case we are getting mod of cot of theta plus 4, theta plus pi by 4, right? So it becomes a little more complicated over here, right? So that's why we avoid this one. So we usually take a square cos 2 theta as the substitution in this case, okay? And now let's talk about some more standard integral formulae which you have to remember. So the first one is integral dx upon under root a square minus x square, and that comes out as sine inverse x by a plus c, right? Now if you remember, we have talked about dx upon under root 1 minus x square, and that comes out as sine inverse x plus c, right? Now what we have done is we have replaced this 1 with a square, and that's why this particular modification, okay? Now, similarly, in the second one, we have dx upon x square plus a square. Now, remember that we have talked about dx upon 1 plus a square, so 1 plus x square, right? And that comes as tan inverse x plus c, right? Over here, what they have done is they have replaced this 1 with a square, and that's why this modification, right? Now, we can see that the first three are more or less similar to the basic ones, right? With some modifications, first three are more or less basic ones. These two are actually new, right? So let's derive one of this one and one of this one, okay? So in the first one, we have integral dx upon under root a square minus x square, and that comes out as sine inverse x by a plus c. Now the basic idea should be to convert this modified form into the basic form and get this formula, right? So how do we do that? We do that with the help of substitution. So let's use this substitution as x equals to at, right? So this becomes dx equals to a dt, right? So this becomes a dt divided by under root a square minus a square t square, right? Now this a and this a gets cancelled out. So we have got integral dt upon under root 1 minus t square. Now if you remember that, this is nothing but sine inverse t plus c, right? Now t is what? T is x by a. So we have got sine inverse x by a plus c, okay? Now in the second one, we have integral dx upon under root x square minus a square. And what do we get? We get ln of x plus under root x square minus a square plus c, right? And how do we do it? We do it with the help of substitution, right? So we take x equals to a sec theta, right? And this comes from here, this one, okay? Now, if we differentiate this one, we'll be getting dx equals to a sec theta tan theta d theta, right? Now this becomes a sec theta tan theta d theta divided by under root a square sec square theta minus a square, right? Now this becomes a sec theta tan theta d theta. We take a as common and we get sec square theta minus 1. Now this and this gets cancelled out. Now we know that sec square theta minus 1 equals to tan square theta, right? So this actually becomes sec theta tan theta d theta divided by under root tan square theta, which is nothing but tan theta only, right? Assuming that we are following the domain restrictions. So this and this gets cancelled out. So what we have got integral sec theta. Now we know that integral sec theta is ln of modulus of sec theta plus tan theta plus c. Now this is our final answer. Now we know that sec theta is x by a. So we can write this as x by a. And for tan theta, we know that tan theta is under root sec square theta minus 1, right? So sec theta is x by a. So we can write this as x square by a square minus 1, right? Now if we take LCM over here, we'll be getting 1 upon a under root x square minus a square, right? So we can write this as over here. Ln of x by a plus under root x square minus a square 1 by a plus c. Now what we can do with the help of log property? We can write this as ln of x plus under root x square minus a square plus minus ln a plus c. Now this can be clubbed as some bigger c, bigger constant, right? So we have got our result. Ln of x plus under root x square minus a square plus some constant, okay? This one. And now let's solve this example. We have integral sine 2x dx divided by under root 16 minus sine 4x. Now if you look at it carefully, you can see that this is of this type, dx upon a square minus x square. Here a is 4 and here x is sine square x, right? So based on this, we can get this idea. I'm not saying this is exactly the same, but basically we have to convert this format into that format. For that, we'll have to again use the substitution, right? So we'll be using sine square x equals to t. Why? Because that would give us t square over here, and also that would take care of the sine 2x dx, right? So if you differentiate this one, we'll be getting 2 sine x cos x dx equals to dt. Now 2 sine x cos x is nothing but sine 2x dx equals to dt. So we have got dt upon under root 4 square minus t square. Now this is the standard format of sine inverse x by a, that kind of format, t by a. So t by 4 plus c. This is our answer. I can replace t over here. You'll be getting sine inverse sine square x by 4 plus c. Okay. And now let's talk about these two standard methods of integration. So the first one is for integration of type integral dx upon ax square plus bx plus c and integral dx upon under root ax square plus bx plus c. Make ax square plus bx plus c as perfect square. Now you must be wondering why are we doing that? So let's try to build that intuition with the help of a process. Okay. So let's say we have integral dx upon x square plus 1. Right. Now this is our very own tan inverse x plus c. Simple, right? Let's say we have dx upon x square plus a square. Right. Now we saw that this becomes 1 by a tan inverse x by a plus c. Now what if I do dx upon x plus 2 whole square plus a square. Right. Now this becomes 1 by a tan inverse x plus 2 by a plus c based on the third property, right? Now if I open up this one, let's say a value is 3 over here, right? A square is 3 square, right? So this integral becomes dx upon x square plus 4 plus 4x plus 3, which basically becomes dx upon x square plus 4x plus 7. Now I can see that this format is same as this format. That's why they're saying you have to make a perfect square so that we can write this one into this kind of format, right? Some x plus 2 whole square or x plus k whole square plus a square, so that we can write down our tan inverse formula, right? Same goes for this one. We know that this is a standard format. This is the penultimate version of standard format. What kind of standard format? This one. So we have to convert the modified version of this one, right? And now if we talk about the second one, what do we have? Now in the second one, we have for integration of type integral px plus q divided by ax square plus bx plus c and integral px plus q divided by ax square plus bx plus c. Write px plus q equals to lambda times 2ax plus b plus mu, right? Now what is this 2ax plus b? Now you can see that this is derivative of ax square plus bx plus c. 2ax plus b is nothing but derivative of ax square plus bx plus c. So why are we doing that? So what are we doing? We are writing this in this kind of format. Basically, in terms of derivative of this denominator, in terms of derivative of this denominator, right? So that we can use that as t or t square over here, and that would be clubbed in dx dt, right? That's how we are going to do over here. And we will try to build the understanding of the second point more clearly through an example. So now let's solve this example. The value of integral dx upon under root 4x minus 3 minus x square is equals to, right? We can see that this is of the type dx upon under root some k square minus ax plus b whole square. Why? Because we have a negative sign in front of x square. That's why this is of this kind of format. Now we know that this format is the modified version of dx upon under root a square minus x square, or in a very crude manner, this is the modified version of dx upon under root 1 minus x square. That is nothing but sine inverse x. So ultimately, we are going to get sine inverse in our answer, right? So now let's try to solve this one. So we have got integral dx upon under root 4x minus 3 minus x square, right? So this becomes dx upon under root something over here minus x square minus 4x, right? And we have minus 3 over here, okay? Now to make this as perfect square, what we can do, we can add and subtract 4, right? Because that would create x plus x minus 2 whole square over here, right? So this actually becomes dx upon under root this minus 3, and we have minus 4 and minus basically plus 4. So this becomes 1 minus x minus 2 whole square. Now you can simply see that this is a very standard format. Now this is nothing but sine inverse x minus 2 divided by a, that is 1 plus c. Simple. D is the correct answer, right? And now let's solve this example. We have integral 5x plus 4 dx divided by under root x square plus 2x plus 5. Now we can see that this is of this second type, this one, right? Now how do we solve it? We write this as the derivative of this one, in terms of derivative of this one, right? So let's say we have fx equals to denominator, that is x square plus 2x plus 5. So f dash, that is derivative of this function, denominator would be 2x plus 2. Now we see that we have 2x plus 2 as the derivative of this denominator, right? Now we have to write numerator in terms of this one. We can write numerator as 5x plus 5 minus 1 divided by under root x square plus 2x plus 5 dx, right? Now this can be written as 5 times x plus 1 dx divided by under root x square plus 2x plus 5 minus dx upon under root x square plus 2x plus 5. Now this is a very standard format, right? Now you have to write this as ax plus b whole square plus some c square, right? And then you can apply the stand formula, right? So this one is very standard. You can keep this as homework. Right? This one is pretty standard. Now let's solve this one. I can write this as 5 by 2 times 2x plus 1, right? What we have done is we have multiplied and divided by 2. Okay. Dx divided by under root x square plus 2x plus 5. Right? So 5 by 2 times integral 2x plus 2 dx divided by under root x square plus 2x plus 5. Now I can see that this numerator has become the derivative of this one. So what we can do, we can take x square plus 2x plus 5 equals to t square, right? Now if you differentiate this one, we'll be getting 2x plus 2 dx equals to 2t dt, right? So what we have got, 5 by 2, this becomes 2t dt, 2t dt divided by under root t square, that is t. So t gets cancelled out. So ultimately what we have got, 5 by 2 integral dt. Very simple, right? So we have got two parts. First one is this part, that is our homework, and second one is this part, right? Very simple, right? So you have to do this in 2 steps according to this particular method, right? So today's lecture was till here only, and in the next lecture we'll be starting with by parts and partial fractions, and that would be the end of indefinite integration, right? So let's meet in the next lecture. Thanks for watching.